Okay, in this lecture I will start the discussion on theory of simple gases. That means we are going to continue towards the thermodynamics of these systems. What are the physical quantities? Now you can use, of course, the microcanonical ensemble or canonical ensemble or grand canonical. You will discover that you can do microcanonical ensemble calculations. It is given in your book in explicit form. Read it. You can apply canonical to classical systems, but it is much better to use grand canonical ensemble ideas for the quantum case. Okay? Fermions and bosons. Well, let me start with the canonical one. I will leave the microcanonical to you. In the canonical ensemble, we can get some expressions and you can use them for, as I told you. Different systems, especially the classical one. Let's do the classical one. That means the canonical approach, canonical ensemble. If we do everything correct, we should get our earlier results back. Here is the partition function. This is an NVT system. In equilibrium, these are constant. It is quite an easy form for the canonical partition function. This is E, energy of the system. Well, single particle states, single particle energies, let's specify them as epsilon, system energy as E. If we do that, we can write the total energy in terms of number of particles in this state with energy epsilon times that corresponding energy, okay, occupation number, formalism as we have done it. And the condition that these numbers must satisfy, occupation numbers, is that when you add them up, you should get the total number of particles in this state, isn't it? Now, this is a restrictive condition, if you like, on these numbers. You have to do all your sums satisfying this restrictive condition. It has to be satisfied. For example, the total partition function can be written as sum over all these occupation numbers. Let me put a prime to show that this restrictive condition should be satisfied in doing the sum. That should be satisfied. G, a number, or that's for any set of these numbers, depending on what type of gas you are dealing with. I will write what these are, and usual e to the minus m e epsilon. Okay, that's the canonical partition function. And this G is the statistical weight factor. Statistical weight factor for the set of occupation numbers and you have to sum over all possible sets of these functions. In these different cases, we have the G function, Bose-Einstein, for example, that must be 1 equal statistical weight for each set. For Fermi-Dirac, we have to have two possibilities. This is 1 if all and E is 0 or 1. If they are restricted to 0 and 1, you have 1, 0 otherwise. You cannot put two particles into the same state. And for Maxwell-Boltzmann case, you have individual terms multiplied by 1 over n factorial. That's the Maxwell-Boltzmann case. Now here we are treating the single particle states as individual states. Okay? We are taking them as individual states. Now let's do the Maxwell-Boltzmann case, which is the classical gas. Okay? And I told you, for quantum, I have to go to ground canonical ensemble, and I will do that in a moment. In the Maxwell-Boltzmann case, classical case, n particle partition function, we have done this before, can be written as 1 over n factorial sum over all single particle energies, state energies, in other words, individual states are considered to be single particle states. It is of this form, isn't it? So this is 1 over n factorial. That is single particle partition function to the power n, as we have done before. Okay? So in that case, here is the result. Well, we know Q1 Vt. We have done that calculation. It is e to the minus beta e. And of course, that means what? Density of states. Turn this into an integral by using density of states. if it is in 3 dimension, it is going by square root of energy, isn't it? This density of states. This becomes 2 pi v h cubed 2m 3s. What I'm doing is to write explicitly this density of states 0 to infinity e to the minus beta e square root energy d. So apart from the function, exponential function, the rest is density of states that is needed to turn a sum into an integral, as we have discussed before. And of course, this comes out to be v over lambda t cube. Huh? Usual classical gas we did before. Lambda t is the thermal wavelength. I don't need to write it again. It is h divided by square root 2 pi m kBt. And the total partition function for the system is v to the n factorial lambda t to the 3n. This is the total partition function. If we know the partition function, we can study the thermodynamics of this, and we did that, remember. Now let's do the Bose-Einstein and Fermi-Dirac gases. These are quantum gases. Bose-Einstein and Fermi-Dirac cases. In this case, well, I have to go to grand canonical ensemble. That is easier to handle because to do a sum with the restriction on the occupation numbers is quite difficult to keep that restrictive condition. So let's go to grand canonical ensemble and write the total partition function in this ensemble, which is ZVT ensemble. And it can be written as n 0 to infinity, z to the n, and canonical partition function. You have to really understand this with the restrictive condition, okay? That prime shows restrictive condition. Of the exponential minus beta sum and epsilon times epsilon. That's it. That's the kind of the double sum. And this double sum can be written overall possible occupation numbers as follows. We can treat them as independent from each other. There is occupation numbers. So we can write them as sum over individual occupation numbers well, let's write this individually as n0 z e to the minus beta epsilon 1 to the power n1, etc. Something like this. That means each occupation number will be added separately. They are treated to be independent from each other. So you can write this as follows. N0 z e to the minus beta e0 to the power n0 n1 z e to the minus beta e1 n1, etc. Since they are treated to be independent, you can do the sum separately like this. And those sums turn out to be simple. Well, it is another representation. Multiplication is shown by P, isn't it? That's the symbol for multiplication of terms. Sum over n z e to the minus beta e p to the power n. Huh? Well, you can do that, but they're independent numbers. They turn into dummy variables, aren't they? All we have to do is to use the conditions and sum, get the summation. Okay? So, this means then, for bosons, where this could be any integer, for Bose-Einstein, let's say, for fermions, it could be 0 and 1 only, Fermi-Dirac. We can do that sum very easily. So, here is the form of the partition function for bosons and fermions. Now, it is really simplified. Here is the partition function, grand canonical partition function for the whole system, which is multiply terms like 1 over 1 minus z e to the minus beta energy for Bose-Einstein. Do the same for Fermi-Dirac, which is 1 plus z e to the minus beta EP for Fermi-Dirac. When numbers can have any value, it is power series 1 over 1 minus x. When it has two values, the sum has two terms in it. Okay? Is that okay? Doing the sum is quite easy, depending on what n1 can be. 0, 1 means to the power of 0 is 1, 1 plus z e to the minus beta e1. Okay. For this case, for convergence, z e to the minus beta ep must be smaller than 1, isn't it? Now, let's continue to get to the thermodynamics of these gases at least get ready for it. Okay? The Q potential, for example, is what is needed to get the thermodynamics. This quantity of the system is Q ZVT, which is PV over KBT. If I take this only as PV, I have the ground potential, isn't it? Divide by KBT, I have the Q potential. In your book, it is the Q potential that is used. That doesn't make any difference as far as I'm concerned. Okay? So this is ln of the ground canonical partition function. Here I don't have to keep the particle number constant. That's the easy thing to do, isn't it? Instead of keeping that number constant, I can allow the exchange of particles between states. So here is the result. This Q potential can be written as, in general form, plus or minus sum over all energies ln 1 minus plus z e to the minus beta e. Okay. Taking logarithm of multiplication of numbers is summing the individual logarithms, isn't it? That's what we are doing. ln A1 times A2 is ln A1 plus ln A2. Since ln 1 is 0, this is minus ln that term. So it is the same form, ln of 1 plus or ln of 1 minus. But in front, there is a minus sign for bosons. So in general, you can also write this as 1 over A, or something like this, sum over all single particle energies, ln of 1 plus A times Z e to the minus beta E, where A is minus 1 for Bose-Einstein, plus 1 for Fermi-Dirac, 0 for Maxwell-Boltzmann. Well, I'm not going to do Maxwell-Boltzmann with this methodology, isn't it? Kind of a general representation. For classical case where A goes to 0, you can write Q, in this case, you can write Q as Maxwell-Boltzmann, Z, sum over all energies, e to the minus beta E, or Z times Q1. And we have done this before. Okay? That's the classical case. Now let's go to the other quantities. If we know the Q potential, we can calculate other properties of the system. For example, average number of particles in the system. If we know Q, we know that quantity 2. For example, average number of particles is nothing but Z del Q del Z, keeping V and T constant. Huh? Since I have the general form, I can write it for both gases rather easily. That turns out to be sum over E, 1 over Z to the minus 1, E to the beta E plus A. Derivative of integral is 1 over the function, derivative of the function. That's what gives this. So, this quantity is minus Z sum over all. Well, let's collectively show the quantum numbers as P. If these are simple gases, we are dealing with plane wave states individually. Then the quantum number is the momentum, or Q number, wave number, whatever. Z to the minus 1, E to the beta epsilon plus A. Minus E to the minus beta epsilon P. We are doing something wrong. I have, instead of this, let's write that explicitly. 1 minus Z E to the minus beta epsilon P for Bose-Einstein. That's negative. And it is Z times sum E to the minus beta EP divided by 1 plus Z E to the minus beta EP for Fermi-Dirac. So I am writing this explicitly, okay, for fermions and bosons. That's another way of writing it, of course. Or simplify as we did. This is nothing but sum over the distribution functions. Fermi-Dirac distribution function and Bose-Einstein distribution function, isn't it? That gives you the total average number of particles in the system. Or writing explicitly the average distribution numbers in this form. Bose-Einstein plus Fermi-Dirac sum over distribution functions. You can get energy of the system as one thermodynamic quantity. Average energy of the system becomes you can get the whole thermodynamics. That's the beauty of statistical mechanics. So here's the average energy. It is defined as minus del Q del beta, keeping Z and V independent variables constant. Okay? And that turns out to be the sum. For Fermi, Dirac, Bose-Einstein, whatever. So it is energy times the corresponding distribution function, average number of particles with that energy. Very simple, isn't it? Multiply the single energies with number of particles in those single energy states, sum them up, you get the total average energy. Eh? Okay, so you can get the rest. What about the pressure? What do you expect for pressure? That's going to be a nice question, I think. We expect some pressure from fermionic gas, but for the bosonic case, we have to think about it. If all of them goes into the ground state, momentum is zero in the ground state, we don't have any pressure, don't we? Very interesting questions. Okay. But when you look at these occupation numbers, average value of the occupation number, which is the distribution function, Fermi-Dirac Bose-Einstein, you see that in the Fermi-Dirac case, this average value cannot exceed 1. Can either 0 be or 1. On the average, it may be less than that. Can you look at that and tell me what's happening? For example, at t equals 0, t is here, isn't it? And there, in beta. At t equals 0, what is the n bar? Fermi-Dirac. Average occupation number. What happens to it? What is this? At t equals 0, k. Well, that z was what? E to the beta times mu, isn't it? We called it alpha. E to the beta times mu, okay, minus E minus n mu, remember. So what happens to that? If energy is smaller than mu, well, at 0K, mu is known as Fermi energy, okay? Chemical potential, the highest occupied energy state. Have you seen this before? You seem to have questions, but I don't know. If energy is smaller than that, what is the e to the minus beta and this difference? E minus something greater is negative, okay? So that goes to 0, and plus 1, 1 divided by this 0 plus 1 is 1. So that thing becomes something like this. as a function of energy at mu, up to mu, it is 1. Above mu, or EF, it is 0. So we have a step function like this. What does that mean? Can you tell me what it means? All the states below the Fermi energy are full. All the states above that energy are empty. Now, if you increase the temperature, what happens, you should know, this goes like that, isn't it? Some of the states above the Fermi energy will be occupied. Some states below the Fermi energy will be unoccupied. Extremely important. Extremely important. So this range is of the order of kBT, thermal energy. So you are giving thermal energy to the particles, they are making transitions to empty states. Huh? You should really understand this behavior of the Fermi-Dirac distribution function. In the Bose-Einstein case, extremely important, we have a condition in the Bose-Einstein case for the convergence of the sum. For the Bose-Einstein case, the condition is Z e to the minus beta e must be smaller than 1, or e to the beta mu minus e must be smaller than 1, or mu minus e must be smaller than 0. That means mu must be smaller than all energy values. When mu approaches the lowest energy state, the chemical potential approaches the lowest energy state, which is the ground state. That means that state starts to be occupied by particles. That means Bose-Einstein condensation. Otherwise, the chemical potential will way down than the ground state energy. So if the ground state energy is 0 energy state, mu, the chemical potential, is always negative. Can only become positive, well, come close to 0. When it goes to 0, then you have Bose-Einstein condensation. Particles start occupying the ground state. They are getting collected into the ground state. Okay? This is also extremely important. Behavior of these particles. Let's remember the case for classical particles, the classical gas. We started to understand what fermions and bosons are doing. Now the classical Maxwell-Boltzmann case, that's extremely important. For all values of energy values, beta times that must be very much greater than 1. That means occupation numbers are very small. in the classical case, that means NE or average values are very much smaller than 1, because it is the inverse of this quantity with a minus sign in the exponent. That means Z is very much smaller than 1. Mu must be negative and very large in magnitude. That must be equivalent to n lambda t cube over v very much smaller than 1, or lambda t is very much smaller than v over n, volume per particle. Volume per particle is a to the cube, interparticle distance, isn't it? So thermal wavelength is very much smaller than interparticle distance. I have underlined this fact before, isn't it? So the quantum effects become important when the wavelength, thermal wavelength, becomes comparable to the interparticle distance. Do you have any questions? Anything you want to ask? Let's discuss. Let's stop here, and from here to the end we can discuss.